Hi, I'm Al-Mahdi Bentafat. I'm a PhD candidate at HBKU Qatar. I'll be presenting our work entitled A Practical System for Privacy Preserving Video Surveillance. The overview of the presentation will be as follows. First, I'll start with the introduction. Then I'll talk about the tools we've used. Then I'll present our system description. I'll talk about the security of our algorithms, and after that I will show some experiments, and I will finish with a conclusion. Location privacy is so important because if people are being tracked for a long period, which is the case with wide-scale video surveillance systems, then we can get a lot of their private information, for example, their home, their workplace, their health, their affiliations, etc. But surveillance systems are being deployed in numerous countries around the world. So basically, an effective video surveillance system automatically monitors all available data feeds, extracts feature vectors from individual targets, compares them against the suspect's database, and raises an alarm when a match is found. Nevertheless, this approach raises significant privacy concerns because individuals can be tracked using their feature vectors. And even if we trust the law enforcement authorities to protect the location privacy of the citizens, the stored location data may be accessed by malicious users such as rogue insiders or attackers or hackers. Because of these privacy concerns, the research community has proposed several methods that provide privacy-preserving systems. These methods execute a secure two-party protocol between the camera and the database server in order to compute an encrypted similarity score, whether Euclidean or based on Hamming distance. These techniques involve cryptographic primitives, including homomorphic encryption, garbled circuits, and oblivious transfer, etc. The problem is the high computation and communication overhead, actually because of the cryptographic layer added to compute the similarity score in a secure manner. In particular, for example, eigenfaces necessitates 40 seconds and over 5 megabyte to match single face against a database of 320 suspects. Also, sci-fi reports 31 seconds for a database of 100 suspects. Another limitation of these methods is that the offline computation is performed for every detected face. Also, these methods provide strict security guarantees. This is a good property to have. So the server will not know anything about the captured face, but this requires very expensive operations to compute the similarity score. So as a result, it's not possible to implement these methods in a wide-scale implementation. So our goal is to design surveillance systems that efficiently and accurately identify suspects through a large-scale video surveillance network. But at the same time, we need to protect the privacy of lawful citizens. We were able to design a system that can operate in near real time in matter of sub-second instead of 30 or 40 seconds to match a suspect. For that, we made some decisions. So the first one is that the database is not held on the server, but the server encrypts the database and distributes it to the cameras. So the encrypted similarity score is computed on the cameras. Even though the cameras are much less powerful than the server, but there are a lot of them. Also, we use one of the most accurate facial recognition algorithms, which is OpenFace. We have only one round of communication if there is no match, and if there is a match, there is very little additional work to be performed. In our case, we don't say that the server doesn't reveal anything. The server will learn something, but that will not reveal any useful information about the captured face. So basically, the server will learn a permutation of obfuscated similarity scores, as we'll see later on. Before moving further, I will just introduce some tools that we used in our work. The first one is Al-Gamal's homomorphic crypto system. An homomorphic crypto system allows performing arithmetic operations directly in the cipher domain. Al-Gamal's crypto system over elliptic curves is an additive system. So if we take the encryption of two numbers, we can perform some operations to get the encryption of their sum. We have used El-Gamal over elliptic curves because of its compact ciphertext. It's only 128 bytes per ciphertext. So basically, to start, a user chooses a private key X and generates public key Q. Then to encrypt a message M, the user uses the public key Q and some random number R. So the encryption of the same message will output a different ciphertext at each time. For the decryption is performed using the private key X, and as we can see, the result is M times Q. So we need to compute the discrete logarithm to get M. But in our implementation, we've used a lookup table to speed up the decryption operation. The second tool we use is OpenFace. It's an open source face recognition and verification system that maps face images to a compact Euclidean space. It's a deep convolutional network trained method for face recognition, and it achieves very high accuracy, 92.95% on the labeled faces in the wild benchmark, which is one of the largest publicly available datasets. The advantage of OpenFace is the face representation efficiency that consists only of only 128 features. And the similarity score between two faces is represented by the Euclidean distance of the two feature vectors. And if the distance is less than a certain threshold t, then we can say that we have a positive match. So the general framework of our system is as follows. So the server extracts the feature vector for every suspect and generates the suspect's database. It encrypts it and distributes it to all the cameras in the city. When a new candidate passes by the camera, it generates the feature vectors and evaluates the encrypted similarity score for every suspect and sends back the encrypted scores to the server. The server then decrypts the score, and the result will be binary, a match or a not match. In case of positive match, a verification protocol is invoked in order to prevent a malicious query from the server. Regarding the assumptions we made in our approach, so we assume a wide-scale surveillance environment. We have a server that holds a database of M suspects and a large number of cameras with moderate computational and storage capabilities. Each individual or suspect Si is represented by an n-dimensional feature vector. With OpenFace, the dimensionality is 128. We assume that the server and the camera are semi-honest. So they follow the protocol correctly, but they try to infer some information about the other party's input. For example, the camera tries to learn the content of the suspect's database, and the server tries to infer some information about the captured candidate face. However, none of the existing methods, none of the existing privacy-preserving protocols, including ours, can protect against illegitimate inputs. For instance, the server can insert an innocent civilian in the database to track him, or the camera can test if a certain individual is part of the database or not, just by using his corresponding feature vector. So first, we needed to convert the float representation of the feature vectors generated by OpenFace. We've used this transformation to get values in the range 0 to 155. By applying this normalization, the accuracy drops very little, only by 0.03%. So now given two feature vectors x from the suspect's database and y candidate vector, the squared distance can be computed as shown. Here n is 128 as a dimensionality, and in the cipher domain, the squared Euclidean distance also can be computed as shown. So as we can see, the values xij square and minus 2xij are part of the encrypted database sent from the server. And in order to speed up this computation, we compute all possible values for a given yi, because yi has only 256 possible values. And even in the case where the camera cannot store all the possible values of yi, we can store a smaller range of values. So we analyzed the distribution of the coefficients of the feature vectors, and we noticed that some values tend to occur more frequently than others. For example, if the camera storage is limited, it can pre-compute only half of the values, for example, values between 65 and 190, and we perform the multiplication on the spot. On the server side, the server needs to pre-compute the lookup table, which allows it to speed up the decryption step. So basically, we store all the possible positive scores. When a camera captures a passing by face, it computes the encrypted similarity score, which is the squared Euclidean distance, then subtract the normalized threshold. Now we can say that if Si is positive, then there is no match. If S is negative, then we have a match. Once the encrypted score is computed, the camera selects two random numbers R1 and R2 to obfuscate the similarity score. This is to add more uncertainty about the reported scores. And here, because R1 is always smaller than R2, then we will not change the sign of the score. So this will not affect the accuracy of the recognition model. The size of R1 and R2 depends on the storage specification of the server. So in order to store 2 to the power 30 values, R1 and R2 must be 11-bit scalars. Finally, the scores are permuted before being sent to the server. In the matching operation, after decrypting the scores, and in the case of a positive match, the server informs the camera of the suspect's position and decrypted score. And if the verification step is successful, then the server can get the captured image of the suspect. So the verification protocol is based on Schnorr's zero-knowledge protocol. Here the server has to prove to the camera that it knows the exact similarity score, and only a server having the right private key X will be able to pass the verification step. Regarding the security of our protocol, it's not possible for the server to link between a given score and a database input. This is only possible if the server is able to reverse the obfuscation and the permutation operations, which is impossible because to reverse the permutations, the server has to brute force m factorial possible permutations. And even without obfuscation, it's very difficult to link between similarity score and a specific suspect. This is because of the unpredictability of OpenFace to generate the feature vectors. So in this figure, we compared 500 images of person P1 against one image of P1, P2, P3, and P4. And as we can see here, there is a large overlap between faces with positive scores, so P2, P3, and P4. We implemented our system on two machines, one to emulate the law enforcement server and the other to simulate the camera operations. Our systems are built on top of OpenFace, which is available publicly on GitHub. We have used Python and C to implement our system, and we used some crypto libraries like OpenSSL. So in this environment, the average time for encryption, decryption, and scalar multiplication is 0.23 milliseconds, whereas the addition is much faster and takes about 0.02 milliseconds. Our code is also available on GitHub regarding the offline phase, we show the computation and the communication costs for both the server and the camera. Here, G represents the database of permuted pre-computed values. So as we said before, the camera can store the entire pre-computation of y times the encryption of minus 2x, or it can only store 50% of the data, and that depends on its storage capabilities. On the server side, the offline cost includes the generation of the feature vectors, the encryption of the database, but the offline time is dominated by the pre-computation of the lookup table. But this is only a one-time cost that incurred before the system becomes operational. So as we can see, the server needs around 32 gigabyte of storage, which is a reasonable requirement for today's servers. And the camera needs around 4 gigabyte to store the entire database G. Regarding the online cost, which is more important because it occurs with every captured face, thanks to the pre-computations in the offline phase, the online time is orders of magnitudes lower than the existing approaches. As we can see, it's below 1 second for a database of 500 suspects. And as we can see, storing 50% of the database G doesn't increase the time by 2, but only 35%. On the server, which is the bottleneck in a wide-scale video surveillance system, it takes only 50 milliseconds for a database of 1,000 suspects. In the figure on the right, we show the communication cost. It involves only a single round, and for a database of 1,000 suspects, the communication cost is only 128 kilobyte. This figure illustrates the round-trip time for detecting a suspect. It includes face recognition, camera encryption, the server decryption, and the required communication time. So for a database of 100 suspects, the round-trip time is 0.8 seconds. While for a database of 1,000 suspects, we need approximately 2.2 seconds. We also implemented our code on a Raspberry Pi to simulate cameras with lower computation capabilities. And as we can see here, with full pre-computation to compute 100 scores, the online computation time is 1.6 seconds. So with more little bit powerful cameras, this time can be significantly reduced. So in this work, we introduced a near real-time privacy-preserving video surveillance system. We performed an extensive experimental evaluation of the two systems, and we have shown that our results are promising. So, for example, for a system of 100 suspects, it takes under 200 milliseconds and just 12 kilobyte too much phase. This work could be also extended further by incorporating GPUs, for example, to speed up the computation on the server side. This is the bibliography of the presentation, and thank you.